All right, students. So today what we will do is this case study is on the topic of moving coil galvanometer. Again, a very important case study and a conceptual discussion on moving coil galvanometer. So first of all, let's read the case study. Let me bring the case study here. Okay, so these are the questions and let me just, all right. So let's read the case study first. Okay. Uh, the galvanometer is a device used to detect the current flowing in a circuit or a small potential difference is applied to it. Okay, so galvanometer is used to detect current, agreed. And when a small potential is applied to it or current flows through it, yes. It consists of a coil, right? So you can see the word moving coil, and therefore it does have a coil with many turns. You know that it is wound on a soft iron core, okay, and it is free to, it's a rectangular coil which is used generally. And it is free to rotate about a fixed axis. So it can rotate about a fixed axis in a uniform radial magnetic field, which is found by using concave pole pieces of a magnet. When a current flows through the coil, a torque acts on it, right? So if you read this, right, it tells you what is a galvanometer. It's a device used to detect the current. What is it made up of? It's made up of coils, okay, with many turns. And these coils carry the current which you need to detect, right? Finally, the current will flow through these coils, and that current interacts with the magnetic field available from the concave pole pieces of a magnet. It's a horseshoe magnet with the two ends as concave pole pieces. Okay, so what does it contain broadly? It contains a coil and a magnetic field in which the coil is there, and coil is the one which is carrying the current, which will come from the circuit in which the galvanometer is measuring the current. It is used to detect current, right? So you have to keep it in series in the circuit. When the current flows through the coil, a torque acts on it. What happens when the coil gets the current from the circuit is it rotates in the radial magnetic field. So this is your case. This is the information available to you. Now the discussion we will have is, now let's go to the questions and then parallelly have discussion on this topic. So let's talk about the question number 1. Okay, so you can see the diagram. Okay, you can see a soft iron core in the middle, and you can see the spring. It's a top view. You can see it from the top, and the coils are like going down, rectangular coils. The perpendicular arms, okay, the perpendicular arms which are perpendicular to what? Perpendicular to the magnetic field. So if this is your coil, okay, and it is getting current from the circuit, right? This is the coil. The coil is getting current from the circuit, is experiencing force on these two sides. So you have this magnetic field, right? And this is your current. This is your current, and this is your magnetic field, B, okay? Coming from the concave magnetic poles. That's a shape which is given to it, okay? So north to south, and these two arms, okay, the arm this and this, which is perpendicular to the magnetic field, experiences force that results in a turning impact, right? So this is the difference, and the torque which it experiences, BINA, right? We will discuss this in detail. So first thing, right, what is the principle of the moving coil galvanometer? Choice A, the torque acting on a current carrying coil placed in a uniform, the torque acting on a current carrying coil placed in a uniform magnet. Yes, if you carry any coil, a loop inside a uniform magnetic field, it will experience torque, no force, because the force is on all the sides. This and this side, the force cancels. This and this side, the force cancels. So no force, but only torque. Statement wise, it is correct. But is it the principle? We need to discuss that. Torque acting on a current carrying coil placed in a non-uniform magnetic field. I think in a moving coil galvanometer, you're using the radial magnetic field. The purpose of radial magnetic field is to create uniformity. So if the coil turns in any direction, the same amount of magnetic field is met by the coil. The current carrying coil never sees a different magnetic field because the alignment of the coil remains always perpendicular to the magnetic field, right? That is why the word radial is very important to understand. So non-uniform magnetic field is wrong, right? If the magnetic field would have been because of the straight conductors, right? So if instead of this you have a straight magnet like this, okay, which is this, right? So even I have not drawn it correctly. The magnetic field I should have drawn should have been bit radial, right? Should have been like this, okay? But what I do actually, this magnetic field is straight, right? Which is not correct. The magnetic field should have been radial, right? Like this. It's a radial magnetic field. As you can see in the diagram also, the magnetic field is like this. And then the radial magnetic field is emerging out like this, okay? So this is your basic diagram. The one which is straight magnetic field is essentially for a straight magnet, right? So this is your north pole and a south pole. This is your coil, and you have magnetic field like this. In this case, the magnetic field is non-uniform, right? Because the coil, the torque will come out to be BINA, right? Sine theta, where theta is the angle between the area vector and the magnetic field. The angle between B and the area vector, which is perpendicular to the loop, will give you theta. Okay, so that will make it non-uniform, right? So the torque will vary as per theta, but it does not vary because we always keep theta is equal to 90 degree. Very important discussion, very important point. The field inside the moving coil galvanometer, because of use of the radial field, is uniform always, right? Because the angle which the coil sees when it moves anywhere, the area vector and the magnetic field make an angle of 90 degrees, right? So you will have maximum torque getting applied in all the situations, right? So you can see the area vector is here coming outward and the magnetic field is here, right? So in any position, this is what it is going to be. So sine 90 always. Potential difference, third choice. What is potential difference developed in the current carrying coil? So it says that the principle is that there is a coil here, okay, this coil. There is a potential difference which gets generated. I don't know. We're not studying electromagnetic induction per se. That is, you know, in the you have d phi by dt like condition. So there is no potential difference concept here. We are referring to basically a torque being applied, the force being applied on a loop. Mutual induction. Mutual induction is a transformer. Wrong choice. So the way I look at it in a short way or a tricky way is uniform magnetic field is a key word for me. I know that moving coil galvanometer has a radial field, and the radial field is basically uniform. So the angle between the loop and the magnetic field is 90 degree. I hope I didn't say 0 degree. The 0 degree is basically the plane of the loop. The plane of the loop is always in the plane of the magnetic field, right? So you move like this, you will find a magnetic field. You move like this, you will find a radial magnetic field. So in any position, the torque is going to be dependent on sine of 90, not sine of 0. Sorry if I said sine of 0. I didn't mean it. Okay. So D is wrong. Potential difference is nonsense actually. Non-uniform is not possible, right? We need uniformity of magnetic field. So the correct answer is A. The correct principle is it's the torque which is produced on the current carrying coil that rotates it in a uniform magnetic field, which is a working principle of the moving coil galvanometer. Let's go to the next question. All right. So if the field is radial, then the angle between the magnetic moment of the galvanometer coil and the magnetic field will be. Now the word magnetic moment, right? So the magnetic moment is basically this part, right? So the I and A, right, is the mu. Mu is equal to IA, right? This part is the magnetic field part of it, right? So torque is also written as mu into B. I think you should know this vectorially also, that sometimes the torque which is being experienced by a loop is given by the vector product of magnetic moment and B. Go and watch my playlist and live classes where I've explained the concept of magnetic moment. It's a very important topic. A lot of students leave this, right? But you should know that magnetic moment is given by IA multiplied by N. And it also makes an appearance in the case of the torque. Okay, so the magnetic moment has a direction also. Again, the direction of magnetic moment. Okay, magnetic moment essentially is north and south pole, right? One side is south, one side is north, depending on right hand rule, the direction and stuff like that. So the magnetic moment is also perpendicular to the loop, and therefore the angle which is between the magnetic moment and the magnetic field is 90 degrees. So you will get mu B sine of 90 again, right? It is one and the same thing that we used BINA sine theta, theta is equal to 90. Even in the torque, which is expressed in magnetic moment, you still write mu into B and get an answer mu B sine 0. So sine 90. So you will get mu, and then you can write mu as NIAB, right? Which I say is BINA, magnetic field. So the correct answer is D. Okay, let's go to the next one. Why are the pole pieces made concave in a moving coil galvanometer? Okay, let's go through each of the choice. Okay, we already know the answer because we've already discussed it, but let's eliminate it. To make the magnetic field radial, okay, it is radial in shape, definitely. To make the magnetic field non-uniform, wrong. To make the torque equal to 0, if there is no torque, how will the how will this instrument work? It is a moving coil galvanometer. If the coil doesn't move, what are we talking about? The coil only moves because of torque. Now I'm confused between the two choices, A and B. I don't know the language. To make the magnetic field radial, okay, to make the magnetic field uniform. See, finally, our job is to, if it is a non-uniform magnetic field, right? It's a non-uniform magnetic field, which means the B continuously fluctuates. Okay, if I have a B which is non-uniform, my torque will actually become BINA, okay, and B will continuously vary, which means that torque will vary. Okay, so if a torque is varying, I don't need that. Okay, I want a constant torque to be applied so that it rotates with a constant velocity because it is connected to a spring, and the expression I get is this, and torque which I get, or the K theta, is equal to BINA, where K is the torsional constant of the spring which is there, which stops the rotation of the coil. I get theta as proportional to I. This is my final goal, right? That I want the deflection to be directly proportional to I. So my answer will be radial is a shape. But what is the aim of radial? Uniform. So my answer will go with B. I want to make it magnetic field to be uniform, then radial. If it is radial but not uniform, what's the point? If it is uniform, I'm very confident that my torque will remain constant because my theta is 90 degree always. I hope that made sense. Okay. Let's go to the next spot. 4. What is the function of the radial field in the moving coil galvanometer? Okay. So, see, the radial field has a function. So, above question, we said the function of the radial field is to make the magnetic field uniform. It should appear identical everywhere. Now, choice number 8, to make the torque acting on the coil maximum. Yes, because if you have the magnetic field which is radial, the torque you will get is not BINA sine theta, which is this. In this case, then you will have a problem, right? The torque will depend on the angle you are. So the torque will become varying torque. Depending on theta, torque will vary. Since you have sine 90 here, you have torque is equal to BINA, right? There is no sine theta in the expression now. So you're independent of the angle. So yes, the torque is maximum, and the magnetic field nature of being radial is helping it achieve that. To make the magnetic field strong, okay, if you take a component of the magnetic field as b sine theta, for example, where in fact the angle is theta is the angle between, I can to an extent say that yes, the b doesn't reduce because we need a good amount of magnetic field, as compared to the magnetic field of the wire. The current carrying wire also produces a magnetic field. The current carrying wire that produces a magnetic field, that magnetic field engages with the magnetic field of the concave poles. So one of the reasons you have a large concave pole is because you want to, have a larger magnetic field coming from the poles, and the magnetic field of the current should be sufficient to interact with it. Although we say that the current interacts with magnetic field, sometimes you also say that the magnetic field of the current should also interact with the magnetic field of the concave pole. But since the B is not B sine theta, so we definitely, can say to an extent that, yeah, it does make magnetic field strong because it is making T as the maximum T possible, this magnetic field. To make the current scale linear, yes, it does help you, right? Because if you write this expression, right, torque is equal to, let me just write it here. So torque is equal to BINA sine theta. Had the field not been radial, you will get this expression, right? And therefore the K theta is equal to BINA sine theta. So here you cannot have theta as proportional to I. You cannot, right? Because you have a theta which is varying. So on both the sides you have a theta, whereas you want a linear scale, right? So which is only possible if you don't have theta here. If you sine theta can be eliminated if theta is equal to 90 degree. So you will get K theta is equal to BINA and theta is proportional to I. How is this being made possible? Because you have a uniform magnetic field which makes an angle 90 degree always with the area loop of the, or with the magnetic movement of the current carrying loop, or the area of the loop, area vector, right? So even this is correct. So you can see radial field makes the field as uniform, and that uniform field is doing a lot of jobs. It is creating maximum torque. And the torque is maximum because theta is 90 degree. The magnetic field is also very strong. It doesn't change. It doesn't reduce, right? It remains the highest possible. To make the current scale linear, you don't have dependence on sine theta. You only depend on theta is proportional to I. That's your aim, a linear scale. All the above. My answer will go to D. All the above. Now remember, you have to do this theory of moving coil galvanometer in detail. Go to my playlist and understand. You should be able to draw the diagram of the moving coil galvanometer, as well as be able to write a paragraph on construction, on working principle, and advantages of a moving coil galvanometer. A very important topic which you can expect that comes is also the current sensitivity. So you should know the current sensitivity calculation for a galvanometer. Okay, and of course the conversion of galvanometer into ammeter and ammeter into the voltmeter. Those questions also come in your entrance examination as well as in your board examination. Okay, let's see if you have any other question. Okay, so one more question. If the rectangular coil used in the moving coil galvanometer is made circular, then what will be the effect on the maximum torque acting on the coil in the magnetic field for the same area of the coil? So you have this rectangular coil, right? You convert it into a circular coil, which is, say, I converted into a circular coil, right? The area of this is A, which is length into breadth, and the area of this is pi r square. Okay, so I have same area. So if you notice, if area changes, what is going to change, right? The coil is still a loop, the area is still there. So change of shape does not change torque. If you go to my YouTube channel, I have put a lot of multiple choice questions. I think around about 1,000 questions by now. And you can see one of the questions I had asked is that if you change the shape of the coil from this to this, even if you keep an irregular shaped coil, makes absolutely no difference, right? So the shape of the coil is not going to decide the torque which gets applied. So my answer to this is A, right? Becomes greater in the circular coil? No. Becomes less in the circular coil? No. Depends on the orientation of the coil. I think the orientation of the coil in the moving coil galvanometer is such that theta is always perpendicular to the magnetic field. So orientation really in the context of a moving coil galvanometer never changes. Obviously, you can bring it up and do like this. That will obviously change the situation. But when we say orientation, we are likely to mean the relative orientation of the coil with the magnetic field. So I hope this helps you understand the concepts of moving coil galvanometer. The conceptual clarity is coming in your mind, and you will be able to solve these questions in your exam. I am going to bring up case study after case study now. Apart from the questions I'm adding to them, you don't need to do anything else. Just listen to my case study, watch my playlist, keep your books alongside, and you will be able to understand the concept on your own, right? I'm giving detailed explanation which nobody gives you, right? So please do subscribe to this channel and spread it in your friends that you have a channel which is giving great explanation and clarity to the students who are facing trouble in physics, right? So thank you very much for your time today, and wait for my next video.